Problem 1.15. In this problem, the pressure difference delta P in a partially blocked artery is called stenosis and is approximated by this given equation. In this equation, we have delta P, which is the difference in pressure, V, which is the blood velocity, mu, which is the blood viscosity, rho, which is the blood density, D is the artery diameter, A naught is the area of unobstructed artery, and A1 is the area of stenosis. We need to determine what are the dimensions of the constants Kv and Ku in this equation. And we also need to determine if this will be an equation that will be valid in any type of units. In order to start this, the first thing that we're going to write are the dimensions for each one of the quantities in the equation. Let's just start with delta P. Delta P is going to be force per area, so it's force length square. We're going to continue with mu. Mu is given as force times length square. We have velocity. Velocity is distance over time, so it's length over time. Diameter is equal to length. Both of the areas have the same dimensions, so I'm just going to rewrite A1 and A. Not that they are the same, but they have the same dimension, so that's why I write them together. And lastly, we have density. Density in the FTL system is equal to force times square divided by length to the fourth. Okay, and we're going to substitute all of these quantities in the equation. The assumption is that Kv and Ku, since they're constant, they're going to be dimensionless, and that's what we want to prove. So let's just start with delta P. So we write delta P on the left side, force per unit length. And then we have equal. We have the equation. So we have Kv as a constant, so I'm just going to write it. And then we're going to replace mu. So let's just start. Mu is equal to force times length square. We're going to multiply by velocity. Velocity is length over time. And then we're going to divide by diameter. Diameter is length. Okay. And I'm going to do the second part. So I'm going to write in another line. We're going to have Ku. And then we're going to have the length naught is length square. The dimension of the other area is length square minus 1. And this is going to be a square. Density is going to be force times square length to the fourth. And then velocity is length over time, and this is a square. Okay, so we're going to take each part individually. Okay, let's just start with the first part. So notice that we have time in the top and time in the bottom cancel out. We have this length, and this length cancels out. And we're left, for this particular part of the equation, we're left with F over L squared. Right? And notice that it's exactly the same dimensions of the pressure drop. That shows you that Kv is dimensionless. Okay, so we're going to rewrite it again in a second so you can see it again. In the second part, we got area over area. They have the same dimensions, therefore they cancel. And we have non-dimension with non-dimension to the second power. So this component is non-dimensional. Okay? And then we see that we cancel. We stay with the F. This becomes this part over here. So if we bring this 2 inside, so this becomes a square, and this becomes a square. Notice that the time square and the time square cancel out. And L squared divided by L to the fourth cancels out, and this becomes L to the second. So at the end, notice once again what we're left with are force divided by L squared. Which is exactly the same dimensions as the pressure drop. Once again, that shows you that Ku is dimensionless. So we write it once again in terms of dimension. We have the first part, the left side, it's going to be force divided by L squared. We got kV. And the component multiplied kV is all force per unit per length square. And then we see that we add this up once again to KU. And we show that everything part in the left side and the right side of this becomes once again force divided by length square. Since the three components are the same dimension, that shows you that KV and KU has to be dimensionless. If not, this equation will not be dimensionally homogeneous. The second part is if this will be valid in any type of unit system, and the answer is yes. Notice that as long as the equation is dimensionally homogeneous, you should be able to apply it to any type of unit system.